Hello, everyone. My name is Rich Ottinger, and I am the Marketing Programs Manager for Park Systems. Welcome to the second installment of Park Systems 2020 Material Science Research, expected to take approximately 40 to 45 minutes, which should allow us some time for a question and answer period at the end. If you click the raise your hand button at that time, I can unmute your line to ask a question. If you would prefer, you may type in your question at any time during the webinar, and I will try to Dr. Rigoberto Advincula. Dr. Advincula is a professor of macromolecular science and engineering at Case Western Reserve University and the editor-in-chief of MRS Communications. He's a fellow of the American Chemical Society and is the author of more than 250 peer-reviewed publications. Please welcome Dr. Rigoberto Advincula.
Well, thank you, Richard, for the generous introduction. And again, I'd like to thank the audience. I hope you're keeping safe and that the current COVID-19 situation is producing positive things. Never mind that a lot of places in the United States or in the world, for that matter, are in lockdown. But I hope and wish you well with your family and your professional endeavors at home. So today I have the pleasure of talking to you about 3D printing using SLA and DLP. And hopefully we will have a good definition of this abbreviation, but also the chemistry, the science, the processing behind these types of 3D printing methods. So first, just to tell you about my affiliation, I was with Case Western Reserve University and still hold a position there. But because of my recent move to University of Tennessee and Oak Ridge National Laboratory, you will be hearing from me from those places in the future. The focus of our research is in nanostructuring of materials, investigation of interfaces, and this type of knowledge, we are able to bring chemistry in nanocomposites and materials used for 3D printing. And you've seen on some of my other webinars and YouTubes describing the talk I gave in Dubai back in November 2016 at the World Economic Forum. That is still true today, that there are many opportunities for 3D printing in many aspects of manufacturing, robotics, tissue engineering, and in many ways, this is a unique convergence for material science and 3D printing and manufacturing at the same time. Now, more recently, I'd like to emphasize and give unique examples how 3D printing has been helping the current emergency situation and pandemic with COVID-19. Now, the use of 3D printing for distributed manufacturing, as well as unique ways to revisit design, improve design, or used to replace parts that are taking a long time to be manufactured or arrive, is one of the interesting things that 3D printing has brought to light. And you doubtless have heard of how 3D printing is used for making face shields, masks, parts of ventilators. More recently, the need for nasal swabs for testing, different types of parts that can be used for ventilators, respirators are emerging needs. So I would encourage you to look at needs and in particular how you can contribute with your interest in 3D printing and materials for the current pandemic situation. So let me start then by reviewing to you a number of methods that are popular, including FDM, fused deposition modeling, stereolithographic apparatus, which we will focus today. That includes digital light processing, or DLP. And along with these two methods, the other important methods include binder jet, powder fusion, SLS, DMLS, and other types of manufacturing methods or 3D printing that extends to metals and ceramics. So this has gone beyond that of prototyping, in that some of them are used uniquely for manufacturing and design of parts or geometries that cannot be addressed with traditional formative manufacturing methods. So let's focus on photo-driven processes that includes SLA and DLP. And let me again remind you that other types of photo-driven processes, including resin, inkjet binding, or delivery of photocurable glue or ink, can also be part of this talk. But I will just be focusing on direct photopolymerization of the matrix material with SLA and DLP. So when we think about polymers, we have many choices. One can think about thermoplastics, for example, where you combine the need for tensile strength as well as cost. And this has to be a trade-off when one is looking for high performance, but of course more expensive source materials. And whether we are talking about thermoplastics, thermosets, or elastomers, the value chain goes on as well. Now, looking at this uh, pyramid of thermoplastics, one can see that a lot of the everyday polymer materials are still based on thermoplastics that are deemed to be commodity. Hence, different types of thermoplastics are high performance, high melting point, and for a reason, they are desirable, but of course, hard to 3D print using conventional machines. Now, in a diagram shown here, which is sometimes called an Ashby type of diagram, one can see properties that combine strength and density, whereas polymers hold its own, synthetic polymers that is. When one compares to metals or glasses, again, one can see that the strength and density are in the middle range as compared to other types of materials, including ceramics and composites. And of course, the form factor that can be addressed based on density can be altered by using foam or aerogel or sol gel materials in order to have a combination of lightweight, low density, and strength as well. So lithography, what do we mean by that? Well, lithography is light patterning. Basically, one associates this term with mask lithography or photolithography, which is very much used in the microprocessor industry. But as a term, one can easily see methods by which you can regulate light, its intensity, wavelength, um, pixelization as a way of controlling photochemistry. So the underlying task here is how to control the photochemistry in a spatio-temporal manner. In other words, one can deal with the same chemistry, but different methods of processing. And as you will see, we have photolithography and photopolymerization around for quite some time. And it's only been recently that it has really been harnessed for manufacturing processes. For example, in the coatings industry, one can be familiar with the term resin or liquid-based resins that includes initiators, oligomers, polymers, different types of components. When exposed to UV light, the coating cures and essentially cross-links. So this base material, which is very well known in the coatings or even ink industry or adhesive industry, is essentially a photopolymerization reaction. In fact, one can think about a visit to the dentist when you have your teeth filling done. Uh, uh, makes use of essentially a photopolymerization method on that composite dental cement. Another way to look at this is comparing between light and heat activated curing. So in many ways, they are related, except that in heat, which can be projected by convection or the use of infrared or near-infrared light, is generated by both evaporative methods, but also by thermally activated cross-linking reactions. On the other hand, UV curing actually depends on the generation of radicals or rearrangement of dye structures, but essentially UV curing or even visible light curing depends on a photochemical reaction that may involve radicals, radical cut ions, or generation of precursors that eventually can be classified as redox or radical initiated reactions. So because of this chemistry, it's been a long time that it has also been harnessed in photolithographic methods. So in photolithography, one can assign the chemistry being driven in thin films, and by the use of a mask or photomask, one can limit the exposure to certain regions. And this has been carried out, for example, with patterning, even with directly assembled black copolymers or self-directed type of structures that goes on towards the nanolithography or nanometer scale. In, let's say, soft lithography, near imprint lithography, these are alternate methods that use mechanical imprinting, but the same chemistry can actually be used to enhance these other types of non-lithographic processes. Hence, the chemistry is essentially a photopolymerization method. So for short, one can use 3D printing in order to extend this two-dimensional patterning into a three-dimensional pattern. And we can distinguish later between a DLP and an SLA. The main difference is that of light projection versus the mechanical movement of, let's say, a laser projected light, where the polymerization takes place at the focal point, or there is a region, and we sometimes call this the box cell, where you have the intense amount of light or directed light where the photopolymerization can be localized. Hence, in combination with a CNC type of movement, or computer numerically controlled movement, one can extend this together with a projection or elevator into a three-dimensional part. Now, in particular, trying to do these things in high resolution will involve a type of nanolithography or even two-photon polymerization, which I'll explain to you in a little while. But basically, the same ingredients comprising of a resin that contains the monomer, the oligomer, and the photoinitiator can be activated by initiation. So in a traditional process where you have linear polymerization, the initiator leads to propagation step and then finally termination. On the other hand, a liquid photopolymer resin actually involves a type of networking process or cross-linking, which can rapidly evolve into gelation and finally thermosetting. So here are some examples of monomers, cross-linkers, diluent monomers that have been used for lithography, but also have been used for 3D printing. Thus, you can see the chemistry is not too remote in terms of connecting 3D printing, photopolymerization with other types of photo-derived chemistries. Now here's a schematic diagram of an SLA process in that the laser light projection can be controlled digitally with a mirror. And as the polymerization takes place on the build plate, that can be elevated, depressed, or raised, and therefore the resin, which contains your monomer, provides the ingredients for the polymerization to take place locally. And of course, the platform, the movement on the z-axis controls eventually the layup or the provision for patterning in the three-dimensional scale. SLA, in fact, can be either bottom-up or top-down approach. So different types of machines are able to control the projection of light from the bottom and the top, and they can have various advantages and disadvantages, including cost savings. So in a way, stereolithography is a vector scanning principle or a mass-based projection. The latter is the basis for DLP. In other words, the exposure of light is simply controlled by the pattern by which it is projected, let's say, from a light source. Very similar to how we use a liquid crystalline display projector or your LCD projector. On the other hand, the vector scanning involves more mechanical movement, which you will see is a plus or minus. But nevertheless, for both methods, the advantage compared to other types of 3D printing is in the high resolution and a wide range of material properties that can be formulated on the resin, meaning you can add ingredients or compounds that can be classified as filler materials, plasticizers, cross-link promoters, or different types of photosensitizers or indirect type of photo cross-linking methods, such as the use of thiolene chemistry. So what are some of the limitations of SLA? Well, one can either look at this as a weakness or a strength in that there's a stair-stepping effect with SLA. In other words, the fidelity of each layer are basically steps or stairs that can lead to a poor resolution, actually, or even different types of um, incapacity to produce edges or different types of geometry limitation. Perhaps the more important limitation is the speed. SLA, since the mechanical platform is given or controlled by time, is actually slower in many ways, even compared to other types of DLP methods. The third thing that one has to pay attention is in the viscosity of the resin, which can change over time because of impurities or byproducts that are produced. Now let's talk about DLP. So the simplest description here is that you have projected light on a resin vat that contains your photopolymerizable material. And then as you start the printing, initiation takes place. The projected light defines the pattern, which can change over space and time. And that as you scan or raise the platform support, the printed material basically grows in layers as you control the amount of light, the intensity of light, and the pattern of light that's projected. This is quite simple in that the only mechanical movement, quote unquote, comes from the elevator. However, one, of course, looks at the micro lenses or things that control the projection of light from the projector itself. Now, talking about different types of innovation, so almost 5 or even um, almost 10 years ago, people have looked at photochemistry and controlling the amount of radicals present or oxygen that quenches these radicals during the photopolymerization itself. So several patents were filed, which eventually led to the clip process. have shown that it is possible to control the speed of photopolymerization by the presence of an oxygen permeable window that enables the initiation to take place, or initiation and propagation, or any control of the radical species present, to limit the polymerization directly at the surface. In other words, it is possible that by controlling quantitatively the amount of quenching species, one can limit the polymerization very much near at the surface. The result is DLP SLA is really one of the best ways to obtain high resolution 3D printed materials and a wide variety of resin compositions that can be used in the industry. Now, the discussion about the speed, discussion about the prototyping versus production is another matter. And one has to pay attention that a lot of these processes, including the clip process, requires a post-curing or optimization technique in order to get rid of the uncured material or monomer, or sometimes require washing to remove any type of unpolymerized material. But nevertheless, maximum strength, and this has been proven again and again, is obtained by a type of post-processing UV thermally driven, or even requiring some bath techniques to obtain the best thermomechanical properties. So it can be quite controversial whether this step actually makes the process slow compared to other 3D printing techniques. Now, one can discuss the parameters that affect 3D printing, and actually the next few slides we will focus on this. So since this is a light-driven process, one can look at the curing depth, the width, the penetration depth of light, exposure, the laser power, the beam radius, the scanning speed. So all of this basically means control of the light source. And control of the light source is very important, whether one is dealing with coatings or two-dimensional printing. In 3D printing, we simply lump this term as a voxelization optimization, which together with the control or the programmability of the 3D printing method matches the photochemistry together with the light effect, or the limitation of light at a specific time or space. So all of this can be optimized, or even the application of artificial intelligence, such that 3D printing parameters can be optimized to any given material. Now, talking about the chemistry, one can classify the compositions as based on the photoinitiator, presence of the cross-linking, oligomer, a monomer or diluent monomer, and then the presence of species like chain transfer agents or even photosensitizers. So the photoinitiator is something that is sensitive to the light source. In other words, this can be wavelength dependent, meaning one can talk about UV wavelength or visible wavelength to basically break up species that generate the radicals. It is the radicals, or the presence of it, that causes cross-linking. And the reason is that in a normal linear chain photopolymerization, you would have propagation to form a linear chain. But the presence of uh, 3 or more functional groups, in the case of a di-cross-linker acrylate system, you actually have 4 links or 4 functional groups. Each vinyl monomer constitutes 2 functional groups. So hence, if you have a di-cross linker, you actually have 4. That is enough to initiate a cross-linking process. So when we say cross-linking, you are hooking up the chains in a network manner. So instead of producing a linear species, they are reacting all over the place. And as I showed earlier, these monomers can be in the form of your acrylate dicross linkers or tricross linkers, and then a monomer such as the ethylene oxide series on an acrylate backbone is actually classified as a monomer diluent because it only has two functional groups. So a lot of this is not new. In other words, the industry or the chemical industry has been familiar with this type of monomers and cross-linkers, which has been used in the coatings industry or ink industry as well. Okay, so this is just a summary of the things I described on the previous page. So let me skip this and instead focus on some of what we call telehelix. So a polymer species or macromonomer species, or even a filler material which contains, let's say, these acrylate groups or even the thiol group, which can uh, have a cascade effect on the photopolymerization method, can be actually part of any material, whether it's a polymer or polymer backbone, or even the nanofiller or filler itself. Essentially, when we say the word telomer or telecalic polymer, these are ingredients that are already existing polymers or macromolecules, yet they have a reactivity because of the presence of the acrylate group. So let's just lump that species as macro cross-linkers or telomeric or telecalic species. The diluent monomer can be in the form of acrylates, methacrylates, acrylic acids, different types of monomers that contain the vinyl group, and that can mean styrenic, pyridinic, etc. So the vinyl group, the acrylate, methacrylate are all related in that they can copolymerize together with each other to form a cross-linker or diluent monomer species. So this can vary in terms of the properties that is desirable. The chain transfer agent is a term that we use to control the molecular weight. It can be used to control the degree of branching or side reaction. A lot of these are based on thiol chemistries, disulfides, which are very effective in transferring the reactivity of the initiator. So in other words, the same thing we have learned with uh, linear polymerization or photopolymerization makes use of this type of chemistry. Now, going back to the photoinitiator, DMPA, a type of acetophenone initiator, is quite popular. Yet one can look at initiators based on benzophenone, redox initiators, peroxide initiators as capable of photopolymerization initiation as well. Okay, so the photopolymerization is again an extension of the addition polymerization of radicals. So one can say that it starts with the initiation, propagation, and termination steps, where the main species are based on the presence of the dicross linker. Okay, so let me just skip this part here and go to other types of methods. Now, I explained earlier that photopolymerization is quite popular. What I mean by this is single photon polymerization. That is, excitation for one photon release is equivalent to one initiation process or generation of one radical. Now, we have another type of photopolymerization which is based on two photon. This has to do with regulation and excitation of light, in which two photons will result in one excitation. And what this means is that one is able to control basically the focal point very precisely, even using confocal type of microscopy methods to regulate the generation of the radical species in a very confined space or time. In fact, my very first knowledge and example of the photolithography process based on 3D patterning is actually two-photon polymerization. And this goes back to almost 20 years ago, or more than 20 years ago rather, where the confocal microscopy and the two-photon polymerization process has been used to demonstrate nanolithography or stereolithography in this um, same chemistry. And some of that can actually be accessed today through commercial instruments such as the nanoscribe. So what this means is that without going too much detail with this diagram, the control of the two-photon polymerization is limited to the generation of, or control rather, of the singlet versus the triplet state in excitation, such as shown in this Jablonski energy diagram. And utilizing this type of control on the pairing of the photons with the uh, excitation, one can use this in the same curing mechanism. So let me digress here first by emphasizing that in a cross-linking process, what you essentially have are cross-linkers or gelators or vitrimers even that are able to react with its neighboring molecule to produce a um, random order rather of network structures which then grows over time. In fact, it is very well known that in a curing mechanism for thermosets such as epoxy or urethane, where a gelation uh, step occurs first, or rather a very high increase in viscosity, which then leads to fixation of these reacted links or cross links into a very static structure such that leads to a thermoset or a hardening. So you have a transition from a viscosity to a modulus driven or bulk process. Now, the same can be said actually of the curing mechanism in the 3D printing photopolymerization. So this rheological phenomena is basically a transition at the gel point of a liquid that increases in viscosity. And then once the gel point has been reached, then the bulk or modulus starts to take over. In other words, you classify this instead of classifying it as a liquid into a solid state material. And hence, the modulus becomes the final or important term. So that this curing mechanism leads to a insoluble solid phase, which is derived from an initially soluble or liquid phase. So in an SLA 3D printed structure, one has to pay attention to viscosity and the including the viscoelastic parameters that determines the cross-linking and vitrification stage. That means that at a certain point during the curing mechanism, there is less free movement of the monomer or the soluble species, but rather from diffusion controlled to kinetically controlled, and then finally a solid state network. So that means controlling this curing mechanism will allow us to control the thermomechanical properties of the material, including prevention of brittleness or increasing the impact resistant properties as well. Now, briefly, let me introduce to you the role of thiol in chemistry. So in a photopolymerization process, this type of chemistry driven by the linking of the vinyl groups can be mediated by redirecting this reaction in the presence of thiol groups. So thiol groups are also able to react with the double bond. And what happens is that this cross reactivity with the thiols provides a better mechanism albeit from a chain growth to a step growth mechanism, where the links between the reactive groups can be more controlled or efficiently distributed over space. The result is the combination of a free radical chemistry and a toluene chemistry is a very good pathway towards better, stronger resins. So I will not bore you with this schematic diagram of how the toluene chemistry redirects the radical, and sometimes it's not only photo but thermally driven towards secondary reaction. So again, going back to stereolithography and two-photon polymerization, how is this different from a traditional one-photon polymerization process? Uh, the chemistry is not too different, except that the direction of light or the voxelization has to be controlled using confocal methods, for example. In a traditional SLA, I mean, the resolution is very good already. You can go up to 100 micron resolution. And as you can see here, very little visibility of the layers that are present, for example, in FDM or other layering 3D printing methods. And the key to this is that the photo density profile is very much fixed at the focal point where the two-photon absorption takes place. So the two-photon absorption reaction is pretty much uh, localized and isolated. And in order to do this, one has to use high-powered lasers, confocal methods, or for example, femtosecond type of pulses that allow you to control the generation of the radical species at that very confined environment. Again, I will not bore you with this equation. I will not bore you with the principle of voxelization, except that one can control the wavelength and exposure time in order to get the best voxel size and hence the printing resolution. So again, there are commercially available instruments, including the nanoscribe that allows one to generate this type of resolution. The result is the voxel can be generated at a much smaller size than 100 micron. In fact, 1 micron to hundreds of nanometers is possible. And again, the use of a high-powered laser, titanium sapphire laser with 780 nanometer allows this voxelization to be done at this resolution. So in a nano-stereolithography method as shown here, the control of the beam diameter, the beam location is very much part of an optimized optics setup with a galvano mechanism with feedback control that allows exposure, time, and phase to be controlled at that limited um, space or high resolution environment. So here are examples of lattice two-photon SLA, very simple. One can pay attention to the lines that are generated, typically anywhere from a few microns to less than a micron. And one can see here, let's say on this chemistry based on a fluorinone carboxylic acid Photoinitiator and a TMPTA crosslinker and a co-initiator as well. So if you carry out this photopolymerization three-dimensionally, one can see that this lattice structure can be extended, let's say, to this level, where patterning then is again based on the control of that mechanical control of that voxelization in the Z scale. On the other hand, multi-scanning paths, different types of feedback control can be used to optimize the projection of this light such that very high resolution, and these are really old images. You can see the literature going back to 2007 or even 1990s where 3D printing basically is represented at the hundreds of nanometer scale as shown here. So with that, I would like to use the rest of my time to focus on nanomaterials and how we've used this together with SLA 3D printing. Nanomaterials represent an added dimension for controlling the thermomechanical properties by using filler materials. And as you can see here, the nanofiller materials comprised of clay, nanoclay, nanofibers, cellulosic nanofibers, and then graphene. A lot of these are commercially available, and many companies are very interested in using these nanofillers to further enhance the properties not only of SLA or DLP printed material, but other techniques such as FDM, SLS, and so on. So take the case of graphene. It's very well known that it can improve the tensile strength with the presence of increasing concentrations of graphene. However, the trade-off can be changes in the impact strength and elongation at break. In our group, we have been doing a lot of research based on techniques like FDM, VSP, SLA, using thermoplastic polyurethane, acrylates, high-performance polymers, incorporating these different types of nanocomposites. And we have published quite a bit since 4 years ago. So one of the first papers that we published was based on using graphene, Oxide, and SLA. To make a long story short, the addition of graphene oxide strengthened the parts, the thermomechanical property of the parts that we produce, as shown in these various geometries. However, what we discovered is the use of thermal treatment actually improves the property of the nanocomposite 3D printed material, where we emphasize the attention toward post-processing techniques. So what happened is that the incorporation of the graphene oxide, which was confirmed by the Raman spectroscopy characterization, allowed us to see how the incorporation of graphene oxide produces different types of hydrogen bonding and cross-reactivity between the um, nanofiller materials and the resin cross-linkers and diluent monomers. What happened was that we did a control experiment where the temperature and curing time together with the amount of graphene oxide showed that by curing or annealing, which we can use liberally as a term, up to 100 degrees Celsius in several hours, actually improve the tensile strength as shown in this graph. Whereas heating it only up to 50% or not heating at all showed inferior properties even with the presence of graphene oxide. We confirmed this because the changes in crystallinity and looking at the DSC and DMA, or the glass transition temperature, confirmed that heating actually reorients the graphene oxide such that we have stronger hydrogen bonding interaction and orientation of the graphene oxide with the resin material itself. And to see a full paper, this was actually published 2 years ago in ACS Applied Materials Interfaces. Another modification we did was to incorporate silicone materials with the Formlab resins. In this case, we use a telecalic poly siloxane polymer, which incorporates the acrylate groups. So we mix this at various compositions with the commercial resin and 3D printed them using SLA. Here is a movie that comes from Formlab showing that the photopolymerization, the 3D printing involves applying or even mixing that resin, and as the object grows, we incorporate let's say in this case, the silicone telecalic. So we are able to produce complex, beautiful parts. Here you can see no difference visually between a 15% siloxane polymer. And you can just imagine that these two complex bro-icosahedron type of structures have different flexibility with or without the siloxane. And this can be seen by the tensile strength testing differences between the two, changes in the elongation at break, yield point, as well as the flexural strength. And depending on the geometry, you can observe, of course, different types of compressibility. Now, let me end by using this last example where we used nanocellulose to incorporate the nanofiller material. Again, in this case, we made our own resin material based on polyethylene glycol diacrylate. The nanocellulose materials are isolated as shown here in the form of whiskers. We mix this with various ratios with the PEGDA resin that contains the Photoinitiator and diluent resin, and then 3D printed them. The result is, again, we obtained different properties depending on the loading of the nanocellulose. What we have observed, as in the case of many nanofiller materials, is that more is not merrier. In other words, we can achieve maximum tensile strength, even flexural and compressive strength, to as little as, let's say, in this case, 0.3 weight percent. So this is very small. The right way to use a nanofiller material is to use it in a small amount. So finally, we then use it to produce a prosthesis device, a type of ear structure that incorporates the nanofiller with the unique tensile properties as shown here. So with that, I'd like to end my talk. And again, I'd like to thank you for your attendance, and I'll be happy to answer any questions.
All right, thank you, Dr. Advincula. We do have one question in so far, so I will pose that to you now. The question is surface tension of the liquid polymer also an issue?
Good question. The surface tension of the polymer is very important during mixing. So when you have mixing of this resin and filler materials, you want them to be as homogeneous as possible, because any phase separation during printing will be a failure in terms of either side reactions or incomplete or inhomogeneous distribution of your filler material. On the other hand, the surface tension is an interesting property which we have observed with surfaces of 3D printed material. In fact, we are coming up with a paper where we change the surface roughness or the shape or geometry of the surface in order to make it either hydrophobic or hydrophilic.
All right, and if anyone else has a question, please type it in to the questions module or click the raise your hand button, and I will try to unmute your line for you so you can ask it. Just give you guys a second in case you have anything you'd like to ask. All right, here's another question. How does the concentrations affect the SPL?
SPL. Okay, so I don't have any definition of the SPL. It's probably a abbreviation of another term that I'm familiar with. But I would just say that the concentration is something where we look at the ratio between initiator, monomer, diluent monomer, etc. There are published literatures that outline an ideal composition ratio between those species in a resin. Of course, one can say that the more initiators you have, the faster the reaction, or the more cross-linkers you have, the more thermosetting the properties are obtained, etc. So those type of optimization on the resin components concentration can play an important role. Again, I would like to encourage the questionnaire to either clarify the question, or you can email me separate and we can do it offline.
Let me see if I can just unmute his line quick and we can get a clarification here. Hi, Jingbo, can you hear me? Would you like to ask your question?
Yes, I'm just want to know the concentrations affected on the nanoparticle size. If you want to produce the films, can you control the thickness?
Okay, that's a very good clarification. So yes, the nanofiller material, and we have worked with a number of them, including graphene, nanoclay, silica nanoparticles. So one is you need to know the nanofiller materials you have. You can confirm that by AFM or TEM even. So the dimension of 100 nanometer to a micron is no problem. A lot of this SLA printing DLP has a layer thickness anywhere from 10 to 150 microns. So the distribution of the nanofillers at that range on these layers is no problem. However, nanofillers are known to aggregate. And if they aggregate, they can produce lumps even up to micron sizes, or non-separated nanofillers. So what I would advise is, as a nanofiller, it's best to use them at concentrations below 1%. If you end up using them at 5%, and especially if you don't see any improvement in properties, then most likely the nanofillers are just aggregating. So I will always like to try 1% and below to have the right percolation threshold and performance cost effectiveness, because after all, these nanofillers are more expensive than the traditional filler materials.
All right, thank you, Doctor. I don't see any more questions. There was one question about getting the slides after this presentation. We will have a video recording of this entire session available on the Park Systems YouTube page and directly on our website, if that would be helpful to you. I would like to go ahead now and ask my final question, which is if you could give us a brief preview of next month's webinar topic, which is 4D printing and stimuli response.
Yeah, Richard, thank you for giving me that opportunity. The term 4D printing is quite intriguing because obviously 3D printing means three-dimensional. 4D, in some definitions, refers to unlocking the fourth dimension or unique property after you've 3D printed the material. So we have seen variations of that in terms of the mechanical response, the chemical response, the electric field or magnetic field response. So I would say 4D printing is an interesting concept because one is able to marry the advantages of the material, the design, and create a transformative object or transformative utility of an object once a field or a stimuli has been applied on a 3D printed object. So I'll be talking more about that. Hopefully you'll see some examples of our work on 4D printing.
Great, thank you. Please join us for that session on Friday, May 22nd, once again at noon Eastern Daylight Time. Thank you all for joining us for this session. You can find more information about Park Systems AFM at parksystems.com, and please direct any AFM questions you have to inquiry@parksystems.com. If you have any questions specific to this webinar series or this session of the series, feel free to reach out to me directly at richard@parksystems.com. Also, I wanted to let everyone know about a new online event series that we will be kicking off later this afternoon. Park Systems live demo and chat sessions will feature Park engineers performing a short live online demo and holding a discussion with attendees. Taking place every week on Fridays at 3 p.m. Eastern Time, the sessions will cover a wide variety of topics, starting today with Park SmartScan topography imaging. Please go to parksystems.com/events/live demo to see upcoming sessions and to register. Thanks again for joining us, and stay safe, everybody.